Welcome back to this unit on practical aspects. We will now talk about how we can empty this hopper that we have filled before. And for doing so, we of course prepare an input script for lights. This input script has this name. And then hopefully we can simulate something like this, that the particles are discharged from this hopper. Here we have chosen to illustrate the particle velocity magnitude in this little movie that we have exported from ParaView. What is important, of course, now we don't have a barrier at the bottom. We don't have an insertion phase because the particles are already in there. We load the restart file from the previous simulation, and a focus is, of course, how can we look at statistics. And what we're going to do is we will print from lights the total mass information in the simulated domain versus time. So to do this, we now look at the input file to lights. We call this in.hopper_empty. Important here, of course, we read the restart file that we have saved before. We again use our include statements to include general information about the simulation. The only real user input here is the time steps that we want to simulate in this emptying phase, which are here 290,000 time steps. Then we have very similar definitions as before for the filling phase. You will not find the insertion, of course, and the primitive wall at the bottom. That will not be the case. However, what you will find here in this input script is this fixed statement here, where we plot to this file the current time information. This is again a variable, and this variable is defined here, cur time. The time is a default variable that is already available in lights, and cur mass again is a variable that we have defined here. Please see the variable command documentation for what this exactly means. Having done that, we are ready to run the simulation. We now open our terminal window, we issue the lights command, this and the input script, we press enter, and the simulation should start. You can now also watch how the hopper is emptying by looking at the current mass in the hopper. Initially, of course, there's a very small change, but then the emptying starts and the number of atoms, the number of particles, and the current mass is decreasing. So the simulation is now finished. Beautiful. We have in this file now the statistics about the time and the mass in the whole system. You see it's steadily decreasing. We can use then any tool of our choice to plot this information. Also, of course, we will find the dump files in this folder as already seen. And at the end, we should be able, similar as for the filling phase, to make plots like this. The illustration of the particles according to their size and the time statistics. So here you see the number of particles in the system as the red line and the particle average velocity as a function of time here on this axis in log scale. We can now proceed and wrap up what we have learned in this unit. First, we have discussed the input to the DEM simulator lights. We have seen that structuring the input in multiple files allows to reuse them. Together with the usage of variables, we can avoid redundancy in the user input, meaning that we don't put the same information twice into the simulator. Also, we have used one input file per phase of the simulation. Specifically, we have seen that for the filling phase we have an input script, and also for the emptying phase we have an input script. If you look closer into the second input script for emptying, you will see that we have reset the time step after the restart command. And this is important because the dump files are numbered according to the time steps. Also, it is important that we always dump our snapshots to a new folder. This is important for good housekeeping reasons. The output from lights can be split up into multiple files. This again is important for good housekeeping. Especially if you run large number of simulations, it's important also to have a smart naming of your folder structure. When you use lights, we heavily recommend you to use PowerView, and there is a dedicated PowerView reader for lights output, which you can find here. This allows you to use the dump custom command in lights, which is quite flexible. Also, you don't need these VTK libraries. If you use PowerView, and we have used a rather old version here, you will see that this is a great tool for taking a quick look at the data. Also, we have seen that basic statistical analysis is possible. In PowerView, such analysis can be activated as so-called filters. What we did not discuss is a very detailed analysis. The reason for this is that it's simply not possible with PowerView, and we need to do this already in Lights, for example, or in dedicated post-processing solutions. For example, if you're interested in particle size distribution or the spatial and temporal averages of, for example, velocities, this cannot be done in PowerView. At this point, I recommend reading the book of Crow et al., where important concepts such as the granular temperature are introduced. As a brief teaser for this, let us consider the situation here on the bottom left. Let us assume we have calculated individual particle velocities, here shown as black arrows. From this information, we can also calculate a spatial average granular velocity, UF here in red. The variance between the particle velocity and this average velocity can then be used to define the granular temperature, which is of extreme high importance for the theoretical modeling of granular materials. With that, I would like to close. I hope you enjoyed it. See you next time.